We're going to look at how we do spectral processing in Nyquist now. As you know, Nyquist has a built-in type for sounds and a fairly complex or rich interface for sounds. There's nothing like that for spectra. Spectra are just represented by arrays of floats. So we have to design some kind of architecture for processing spectra in Nyquist. And the way that works, from a data perspective, we're taking input sounds, which is shown on the right, extracting overlapping windows, applying FFT to those windows to get spectral frames, and then we turn those spectral frames back into time domain frames of samples, overlap, add them, and produce an output sound. So that's the chain from time domain to spectral domain back to time domain. In terms of control flow, everything is done in a lazy or demand-driven manner. And so that means we start with the output on the left. When we need more output, we generate a request to the object that's providing samples, and it generates a request for a spectral frame that it needs to do an IFFT. The spectral frame generates a demand to the sound to produce another frame of samples, which can be Fourier transformed into a spectrum. So that's kind of how the computational flow works. If we want to do actual spectral processing, we need to put something in the middle of all this so that after we generate a spectral frame, we can do some computation on the frame and then return that frame to the inverse Fourier transform to turn it back into sound. So we're going to do this in an object-oriented way where we essentially have an API or an interface to these objects that we can then place into the processing chain. In fact, we want to make this general enough so that the objects could perhaps pull spectral frames from multiple sounds. A common thing to do is multiply them together to get a kind of convolution of sounds. The object behavior we need looks like this. We define a method called next, which produces a frame, and our objects in turn can send next methods or invoke next methods on other objects to retrieve frames. SAL, unfortunately, does not have a rich object-oriented flavor, and but SAL is built on top of XLisp, a dialect of Lisp, which does in fact support objects. So what we're going to do is implement some libraries in Lisp that can be called upon by SAL to generate objects and to customize their behavior. So the way this works is we have a kind of a generic custom object, and part of the state of that object is a function to call to invoke some behavior, and that function can be written in SAL. And there's also state in this object that will be passed into this SAL function as parameters. So that way we don't really need any special syntax to declare objects. We'll just sort of parameterize a generic object with SAL functions. And this SAL function needs to be able to get frames. We're actually going to compute frames, request frames automatically from a source, but if there are multiple sources, we'll provide an SA next function for spectral analysis next, which will get the next frame from some source. So here's some kind of skeleton code to show how this whole system works. We have a function called SA_init for spectral analysis init, and it has a number of keyword parameters, an input file or sound, the duration of the FFT in seconds. So take the number of points of the FFT and divide by the sample rate. There's a skip period, which is how many samples. So in this case, 512 is a 8-way overlap, and a window function, which would probably be this constant Han for a Han or Hanning window. So that creates an analysis object, which returns spectral frames. Now we want to define an object that will actually do some processing. The simplest thing I could think of for an example is to do some spectral processing where we just eliminate the zero element, or in other words, the DC component of the signal. It's probably not the best way to implement a DC removal operation, but at least we can go through the motions of doing some spectral processing. We define a spectral processing object using SP init, and we pass into it a source of frames. So this is a spectral analysis object that we created on the previous slide. Then we specify a sal function that will be called for each frame, and we can put some state into the object. And so we hand off the initial values of the state. Once we do this, the spectral processing will consist of, first of all, the system will automatically analyze the next spectral frame from the spectral analysis source, and then it will call this processing function. Here's our processing function. The first parameter is the spectral analysis object itself, which probably you don't need because the system is automatically going to extract the next frame of that analysis object and pass it in as the frame parameter. And then this P1 and P2 are just these state values that we passed into SP init. What you do is you process this frame, and again, our processing example here is going to be extremely simple. We're just going to remove the DC component by setting frame sub 0 equals 0. And then be careful about the return. We want to return not only the frame after processing or constructing a new frame, whatever, but we also want to return the new values of the state of the object. So if the state doesn't change, just return P1 and P2 in this list. If you want to, P1 might change. There's an example in the code we provide where part of the state is just a counter that counts how many frames, and so the return value here is P1 plus 1. All of these things, the frame and each element of the state, are packed into a list, and that's returned from the processing function. And then the actual underlying object retains the state and prepares to call again when the next frame is needed. Finally, once you've set up this SP object, we have a function called SP to sound, which will do the spectral analysis and reconstruct a sound from a sequence of frames so you can actually play it. In spectralprocess.sal, there are examples of various kinds of spectral processing. Notice that this requires spectralprocess.lisp and spectralanalysis.lisp as well. I want to point out an interesting thing that people do with spectral processing, and this falls under the name cross-synthesis or morphing. In general, you're combining features of two sounds. So a common approach is that you separate sounds into an excitation part and a filter part, and you combine the filter of one signal with the excitation of the other. And we'll talk more about this later in the context of vocal synthesis and vocal processing. But an example is, imagine that what the voice is doing is filtering sound, and so you could apply the vocal tract filter to noise or the sound of an orchestra, etc. Or you might take the cello body and apply it to a source, which is a woodwind sound. And there's some examples of this in spectralprocess.cell.